Section 6.7. Adding null bits. This idea of mixing bits of the message with null bits can also be done without embedding the message in an image or other file, and it can be done by hand. First, encipher the message using simple substitution or any method of your choice. Write this preliminary ciphertext in binary, say 5-bit binary. The simple substitution and conversion to binary can be done in one step. You could just substitute 5-bit numbers for the 26 letters of the alphabet in some mixed order, like this. Notice that there are 6 decimal digits in addition to the 26 letters of the alphabet. The digits 0, 1, 2 and 5 are omitted to prevent confusion with the letters O, I, Z and S when handwritten. This gives you the 32 characters necessary to convert the 5-bit numbers back into symbols for transmission. Now that the message is in the form of a bit string, the null bits can be added. A selection key is used to specify where the null bits are inserted. The selection key has the form M1, N1, M2, N2, M3, N3, which means take M1 bits of the message and insert N1 null bits, take M2 more bits of the message and add N2 more null bits, take another M3 bits of the message and add N3 more null bits, and so on. Here is an example using the selection key 213142232. With this scheme, message is enciphered as Q9JIF PGUFF F. 4 null bits, the shaded bits, are appended to complete the last group of 5 bits. This is called padding or null padding. The selection key could also be given in binary form, say 11011110011100. Each 1 bit in the key means take the next message bit, while each 0 bit means insert a null bit. This scheme is stronger when 2 different alphabets are used for changing the letters to bits, and for changing the bits back to letters. The strength is also improved by using variable length substitutes like the Huffman codes described in section 10.4. For this purpose, the lengths of the codes need not correspond to the frequencies of the letters, but they still must have the prefix property so that Reaver can decipher the message. You can avoid the need for adding extra characters for the second substitution, which goes from bits back to letters, in 2 ways. 1. You could take the bits in groups of 4 and use only 16 letters of the alphabet, or use the 16 hexadecimal digits. Or 2. You could use a variable length code with 6 4-bit code groups and 20 5-bit code groups. Again, these code groups must have the prefix property. Here is an example. Notice that I used 4-bit substitutes for the 6 highest frequency letters. This will make those 6 letters have about twice the frequency in the ciphertext as the other 20 letters. This could make an unwary opponent believe this is an entirely different type of cipher. Adding null bits is applicable to many types of encipherment. Since a null bit is indistinguishable from any other bit, adding null bits is stronger than adding null characters. It can increase the rating of a cipher by as much as 3. Let's look at a specific example. Call it cipher null 5. As earlier, there are 3 steps: convert from letters to bits, add null bits, and convert back from bits to letters. Letters are converted to bits using homophonic substitution, from letters to 5-bit groups. 2 substitutes are provided for each of the letters E, T, A, O, I, N. Null bits are inserted using a selection key, as in section 6.6. Bits are converted back to letters using a 4-bit/5-bit substitution, like the previous table. Cipher null 5 is rated 6. Section 6.8. Merging multiple messages. The binary form of key can also be used as a merge key to merge two messages. That is, the bits of two messages are interleaved to form a single message. A merge key in base 3 or base 4 could be used to merge 3 or 4 messages. A base 4 merge key could likewise merge 3 messages plus null bits. Two advantages of merging multiple messages are that you don't add as much extra length as using null bits, and you can use simpler, faster encryption. If you interleave 4 messages with a long merge key, and you use a different simple substitution for each message, that alone gets a rating of 5. If you perform an additional simple substitution on the merged message, the rating increases to 8. The keys for merging messages can take two forms, a bit count form or a selection form. In the bit count form, the messages are taken in rotation. Each digit of the key specifies how many bits are taken from each successive message. In the selection form, the messages may be taken in any order, but only one bit is taken each time. Each digit of the key specifies which message to take the next bit from. These examples show how the messages 01010111010001101011 and 1110101100111010 are merged by the bit count method using the key 123123 and by the selection method using the key 12122112. Merging multiple messages may be messy when the messages have different lengths. You need to have an end of message marker on all but the longest message. Another way of dealing with non-matching lengths is to balance the merge. Begin by writing all of the messages end to end, separated by some reserved character or character sequence. Then simply divide this long string into equal parts. For example, if the messages have lengths 50, 60, 70 and 80 characters, that is a combined length of 260 characters plus 3 separators for a total of 263 characters. You could divide that into 4 strands of 66, 66, 66 and 65 characters. If you are using 8-bit bytes, you could divide the 263 times 8 equals 2104 bits into 4 strands of 526 bits each. It is not necessary to split the bit string on even byte boundaries, but you should choose keys that take an equal number of bits from each strand. Incidentally, the number of messages and the number of strands are independent. There can be one message or many, and any number of strands from 2 up. For example, one message could be divided into 3 strands, and 3 messages could be divided into 2 strands. Balancing is half the solution. The other half comes when you get near the end of the merging process. Eventually you will have merged all the bits from one of the strings, while the other strings have bits left. If the merge key specifies another bit from a string that has no bits left, just skip to the next bit selection. Let's pull all of this together into one cipher, which can be called merge 8. The merge 8 cipher operates on one or more messages concatenated end to end. In the base 26 version, the 26 letters are converted to binary using a 4-bit/5-bit code, like the 4-bit/5-bit substitution in section 6.7. The message divider can be a letter sequence such as XXX or END. In the base 256 version, a well-mixed keyed simple substitution is applied to the ASCII code. The resulting bit string is divided into 8 equal-length strands of bits. A key of 32 octal digits is used to merge the 8 strands. Each of the 8 octal values appears 4 times in the key, So there are 32 factorial over 4 factorial to the power 8 equals 2.39 times 10 to the power 24 possible merge keys. A second simple substitution is performed on the resulting string. An 8-bit substitution is used for both the base 26 and base 256 versions. Merge 8 is rated 6. Section 6.9. Embedding a message in a file. When a message is hidden in a picture file, there are at least 7 bits of the image for every bit of the message. That's mighty inefficient. You can hide a lot more message bits in a file if you don't try to make it look like something else. It's a ciphertext, so let it look like a ciphertext. There are dozens of ways to hide a plain text message inside a file. I will simply list some of the options. As in section 6.6, for each byte of the file, a certain number of plain text bits are hidden among the 8 bits. A fixed number of plain text bits or a variable number of plain text bits are taken each time. The bits are placed in fixed bit locations or variable bit locations within each byte. The bits are placed in order or rearranged. The plain text bits are inserted as is or lightly enciphered, for example by simple substitution. The ciphertext bits are left as is or lightly enciphered, for example by simple substitution. The number of bits, the locations of the bits, and the order of the bits can be controlled by either a periodic key or some random sequence. Depending on which options are chosen, ciphers in this class may be rated anywhere from 1 to 10. Here is an example of such a cipher. 1. Perform a well-mixed keyed simple substitution on the message. 2. Using a pseudo-random number generator with a large internal state, choose 2 to 6 bit positions in each byte. Place the next 2 to 6 bits of the message, in order, into these 2 to 6 bit positions. Set the remaining bit positions to random values. 3. Perform a second well-mixed keyed simple substitution. This method, called embed bits, is extremely fast and simple. The downside is that the ciphertext is about twice as long as the plain text. Embed bits is rated 8. To bump the rating up to 10, replace the simple substitution with a bigram substitution, such as 2 square.